Okay, hi Zach. Welcome to lesson number 99. This lesson starts on page 418 in your book. We are almost, look at the book right now. We only have a little bit left in this book. This is so awesome. Today's lesson is going to be great. We're going to talk about uniform motion, which you've been doing. Distance equals rate times time, right? And we're going to talk about unequal distances. So what if there are two objects, but they go a different distance? That's what these problems are going to be about today, and you're going to understand it right away. So no problemo. All right, here's something to think about. If 666 really is the most evil number in the world, then 25.8069 is the root of all evil. Get it? It's the root of all evil. Okay, let's get started in today's lesson. So it talks about how sometimes when you have a uniform motion problem, it tells us that one person or one thing traveled a distance that is different than another person or another thing, and it might be greater than another person or another thing. And that is no problem. We can figure it out because we're going to draw a diagram like this. It's going to take one of the following forms. Okay, so let's start with this one. You can still do a drawing. Here's the starting point. Here's the end point. Distance P went this entire distance from this starting point to this end point. But distance A looks like it stopped short, and it might give you a number like 50 feet or 50 farther, whatever units. So dP went 50 units farther than dA. So if you draw a picture like this, then you won't get messed up by these problems. And then you can write something like this: dA plus 50 is equal to dP. And if you draw it out, then you'll never get it wrong, because what some people do wrong is they add that 50 to the wrong side. They might say, oh, dP went 50 further, so I'm going to put the 50 over here. No, that is wrong. If you draw the picture, then you can see that dA plus 50 is going to be equal to the distance that P went if the distance of P is further, right? So on this picture on the left, they both started from the same place, and P, distance P, went 50 farther than A. Now let's look at this picture on the right. In this picture, A, I didn't label this, so let me just label it really quick. This is distance A right here. A started out 50 feet in front of P. So they didn't have the same starting place. Distance P started here, distance A started here, and it was already 50 further than distance P. And then they both ended up at the same place. So in either case, the left or the right, the distance A plus 50 is going to be equal to the distance that P traveled. And the equations are going to be the same. And so you write an equation like this: dA plus 50 equals dP. And then, since you already know that distance equals rate times time, you can change this equation right here to rate times time of A, because all I did was take distance equals rate times time, so I changed the distance of A to rate times time, plus 50 is equal to distance equals rate times time, this time of P. So this, you'll either use this equation or the combination of both when it's something like that. Okay, so thank you for watching a stupid movie with me on Mother's Day. That was super sweet for you to watch a chick flick. And you know I played the Mother's Day card on that one, so that's just a reminder of how nice you are, and that if you study hard, anyone can get into Harvard Law. Okay, let's jump into example 99.1, all right? And it says this: at 8 p.m., Achilles, that's cute that they called his name Achilles, he left camp and he headed south at 20 kilometers per hour. So I'm going to start keeping track of some of these things. I'm going to write, let's see, All right, the rate, because they gave us the rate of Achilles, is equal to 20 kilometers per hour. Okay. And then at 10 p.m., Pat headed south from the same camp. If Pat was 50 kilometers ahead by 3 a.m., what was his speed? So they did give us some times here, So they had 8 p.m., 10 p.m., and then 3 a.m. And they want to know, what are they asking for? The speed of Pat. So they want to know the rate of Pat. Once you get the rate of Pat, that's the answer to the question. That's what they want to know. Okay, so let's draw a picture to see what's going on. Did they start out at the same place? If they did start out at the same place, my arrows are going to start right here. And it sounds like they did, because this is camp. So Achilles left camp, and he headed south at 20 kilometers an hour. So this is the distance of Achilles. Okay. And then Pat headed south from the same camp. And who's ahead? Pat is going to be ahead. So this is, let's see, this one is where Pat ends up, because he's the one that is ahead in terms of distance. So I'm going to put this is distance P for Pat. And it says, what does it tell us about distance? Pat was 50 kilometers ahead. So where do we put the 50? We put it here, 50 kilometers, because Pat, when he gets to this point, is 50 kilometers ahead. That's that 50. So if Achilles had gone another 50 kilometers, he'd be the same as Pat. And then it wants to know what is his speed, which is asking what is the rate of Pat. Okay, so, I changed the name from Patroklos, which is probably something related to Achilles. I don't know, but I just changed it to Pat to make it simple. Okay, so Pat went 50 kilometers farther. So how do we write this distance equation? Let's start with the easy distance equation, okay? We're going to do distance of Achilles plus 50 equals the distance of Pat. Now, let's substitute, since we know that distance equals rate times time. We're going to substitute rate times time whenever there's a distance. Okay, so let's do rate times time of Achilles plus 50 equals rate times time of Pat. Okay, now let's reread the problem to get the rate and the times right, okay? So I already did the rate because I wrote that down when we read it the first time. So the rate of Achilles is 20 kilometers per hour. But what else do we need? We need, so we're looking for this. So everything else, we're going to need to figure it out. We need to figure out TP, TA, and we know RA. Okay, so let's write down our knowns. The rate of Achilles, I already said, is 20 kilometers an hour. We also need TP. We need TP. The time of Pat. So let's reread the problem and see if we can figure out Pat's time. So it says he started at 10 p.m., he heads south, and then he goes until 3 a.m. So if we count 10 p.m. to 3 a.m., 10, 11, 12, 1, 2, 3, that's going to be 5 hours. So time of Pat is 5 hours. Okay, what's time of Achilles? It's not the same time because let's read the problem again. He leaves camp at 8 p.m. and then we're going to go from 8 p.m. to 3 a.m. So basically 2 hours earlier, we're going to add 2 hours from Pat's time. So the time of Achilles is 7 hours. Okay, so now Easy peasy. All we need to do is substitute everything in and solve for the rate of P. And if you want, you can change this equation up here. Divide by TP. Then, well, I basically divided both sides by TP. This cancels out. And so the rate of P is equal to all of this. So I'll write it down in a different way. Rate of P is equal to RATA plus 50 over TP. Now let's substitute everything in. 20 times 7, that goes in parentheses because it's this part, okay, plus 50 over TP, which is 5 hours. And we get R of P is equal to 38 kilometers an hour. And then I like to go back and see if that makes sense. So the rate of P is, whoa, oh shoot, I don't even know how I did that. That was weird. 30. So does it make sense that Pat was faster? Yeah, because he started 2 hours later and then he went this whole distance. So if he's 30 and RA is 20, yeah, that totally makes sense. Or he's 38, I guess, 38. All right, cool. Let's go to the next example. And I put this one because it's more of a show you would like instead of the silly one we watched yesterday. Okay, let's do example 99.2. All right, Rachel. We're talking about Rachel now, has a 15-kilometer head start on Charlene. So we're going to draw our picture. Here's the starting point, and here's the end point. Okay, how long will it take Charlene to catch Rachel if Rachel travels at 70 kilometers per hour and Charlene travels at 100 kilometers per hour? Oh, this is an interesting one. Okay, so when it says, how long will it take Charlene to catch Rachel, that means they're going to be at the same place in time. So that's this one. But you can kind of think about the head start as, well, they didn't start at the same place because Rachel had already been going before Charlene even started. So when Charlene starts, Rachel is already here. And it gives you this distance. So when we draw a picture like this, we're talking about distances. We can't just put in a rate, but you can put in a rate times time because that's the same as distance. Okay, so Rachel this is Rachel, she has a 15-kilometer head start. So she goes this distance and then Charlene starts running. All right, so let's figure this one out. They end up in the same place, but Rachel started 15 kilometers ahead. So the distance diagram looks like this. If you can get to this point and figure out the distance diagram, then you'll get it right. Because from there, we're going to write our distance equation. How do we make this equal? How do we make this whole distance equal between the two of them? And what you do is you do 15 plus the distance of Rachel, because we're making this line equal to this line. That's all we're saying when we do our distance. This line is equal to this line. So 15 plus this distance is equal to the distance that Charlene went. Okay, so now we replace distance with rate times time. Okay, so we're going to write 15 plus rate times time of Rachel is equal to rate times time of Charlene. Okay, now let's reread the problems, because the other thing I like to do from here is try and figure out what are we solving for. Okay, so let's reread the problem and figure out what we're solving for. Rachel has a 15-kilometer head start. How long will it take? So we're looking for a time. How long will it take Charlene? So we're looking for time of Charlene. That's the question mark. Okay, and it gives us, let's see, it gives us a couple rates. Okay, so the rate of Rachel, let's do the rate of Rachel. She's going 70 kilometers per hour. Kilometers an hour. And Charlene, it gives us that rate. The rate of Charlene is 100 kilometers per hour. Okay, the other thing that we don't know is the time, because we need distance equals rate times time. What's the time of Rachel? The time of Rachel has a 15-kilometer head start. Okay, so it doesn't tell us the time of Rachel, but it does tell us that they're going to catch up. And so she's running this whole way, but she's running slower because she got that head start. So what we know is that the time of Rachel is going to be equal to the time of Charlene. How do we know that? We know that because, how do I explain this? We know that because it's kind of like if you're starting a stopwatch, you start it when Charlene starts here. It's like this time doesn't really, it's like time starts here for Charlene and time starts here for Rachel. So, but they're going to catch each other. So they end up here at the same time. Because when will one of them catch the other one? When the time is the same. Yeah. Is that a good? Is that a good explanation? Okay, text me and tell me if it's not a good explanation. But basically, if you're talking about one person catching another person, you can start the stopwatch here when the second one goes, and their time is going to be the same because this person's going faster. All right, if you don't, maybe that's totally obvious to you. All right, so let's plug in everything that we know now. Okay, so now we have all the unknowns except for Charlene's time, which is what we're solving for. So we're going to do 15 plus rate of Rachel, which is 70 times the time of Rachel. And since we don't know that, we're just going to put TC. That way we have only one unknown because that's what we're solving for. Equals the rate of Charlene, which is 100 times the time of Charlene. Now we have an equation with only one unknown, even though there's like two there, because they're the same thing. They're both the same unknown. Okay, so here we just use the fact that TR is equal to TC. Okay, so let's simplify this. 15, let's subtract 70 TC from both sides. So 15 is equal to 30 TC. And then divide by 30, that cancels out, divide by 30. So TC is equal to 15 over 30, which simplifies to 1/2. So and the units are hours because we were doing kilometers an hour. So the units are hours, so the answer is in a half an hour, Charlene will overtake or will catch up with Rachel. Okay, one more example and then we're done. We are done. Okay, example 99.3. Harry and Jeanette jog around a circular track that is 210 meters long. Jeanette's rate is 230 meters per minute. Harry's rate is only 200 meters per minute. In how many minutes will Jeanette, be a lap ahead, a full lap ahead? Okay, I guess I didn't finish writing that out, sorry. Okay, so what we're gonna do is we're gonna draw the picture first. And we're gonna ignore the fact that it's a circular track and just straighten it out and make it straight, okay? So it says that Harry and Jeanette jog around a circular track that's 210 meters long. But it wants to know, when will Jeanette be a lap ahead? So let's start with Harry's distance. Harry's going to go some distance. And Jeanette is going to be further because she's going to be a whole lap ahead. And how far is a lap? A whole lap is 210. So this is the distance Jeanette went. This is the distance Harry went. And Jeanette is going to be a lap ahead. So one whole lap is 210. This is the lap ahead. Okay, so make sure that you draw the pictures on these and make sure that you get the picture right. If you get the picture right, you'll get the whole thing right. Because then all you have to do is write the equation. This plus this is equal to this. Okay, so DH plus 210 is equal to DJ. And then you're going to use the equation, distance equals rate times time. And you're going to substitute rate times time anywhere there's a D. Okay, so we're going to do rate times time of Harry plus 210 equals rate times time of Jeanette. Okay, so let's go back to the problem and pick out all the things that we know. And I just like to start with, what are we solving for? Because if it tells us, if we know what you're solving for, then you know all the other things that you have to look for. So what did they ask that we're solving for? In how many minutes will Jeanette be a lap ahead? So minutes of Jeanette. So that's time, let's get a different color. Time of Jeanette is the unknown. Or you could think of it as time of Henry. Let's see. In how many minutes will Jeanette be a full lap ahead? Yeah, they're actually going to be the same time. Because when will they be at this point? And this point means that it's like he stopped here. And then when she finishes here, when Jeanette finishes here, he's just still going to be sitting here, but the times are going to be the same. Okay. All right, so if we're solving for TH, let's say, then we need to figure out what is RH, what is RJ, and what is TJ. So what is the rate of Henry? The rate of Henry, let's go back to the problem. Okay, Jeanette's rate is 230 meters per minute. Harry's rate is 200 meters per minute. So it just tells us straight out. Okay, so rate of Harry is going to be 200 times TH plus 210 is equal to the rate of Jeanette, they gave us that, is 230 times the time of Jeanette, but since these times are equal to each other, then I can just substitute TH. Now I've got one equation, basically one unknown. So let's solve this problem. Minus 200 TH from both sides, minus 200 TH, and that goes to nothing, and I have 210 is equal to 230 minus 200 is just 30 TH. Then let's get this little girl out of the way. Then let's divide by 30. That cancels, divide by 30. TH is equal to 210 over 30, which simplifies, let's get rid of those zeros, 21 divided by 3 is 7. And what's our units? They told us the rate in meters per minute, so the units is minutes, not hours this time. You have to get the units right. That's important, or you don't get the problem right. Okay, so Jeanette's going to be a full lap ahead of Harry in 7 minutes. All right. Yeah, you can solve these problems. And no, that doesn't make you a nerd. That makes you super smart. Maybe a little bit of a nerd, but, well, it depends on how much you enjoy it, I guess. But it should be enjoyable. Hey, embrace your nerdiness. Okay, have fun doing your math. Zach, love you. Bye.